Welcome, my friends. I'm so excited because in this video, we get to talk about the confidence interval for proportions. So let's go ahead and get started. Now, in the last video, we talked about how to construct a confidence interval to estimate the population mean. But the only way you can calculate the mean is if you have quantitative data. If you have categorical data, we can't calculate the mean. Here's an example. A February 7th, 2022 poll found that 685 out of 2005 registered voters could locate Ukraine on a map. The possible outcomes for this variable are either yes or no. Each individual could either yes, locate Ukraine on a map, or no, they could not locate Ukraine on a map. So that makes this a categorical variable. The most common way to summarize categorical variable is to calculate the percentage or proportion of successes to the total sample size. In this example, we can calculate the proportion of voters sampled who can locate Ukraine on a map, which is represented by the symbol p hat, by taking the number of successes, in this case the 685 individuals who could locate Ukraine on a map, and dividing by the total sample size of 2005. We'll get 0.3416, or about 34.16%. From our sample, about 34.16% of the individuals could find Ukraine on a map. But of course, this number probably does not perfectly represent the population proportion, which would be based on all registered voters. This was only a sample of 2005 registered voters, so this number is probably a little bit off from the true proportion. In order to find the true population proportion based on all registered voters, we would have to have a census of all of the registered voters, but most likely that's going to be pretty unrealistic. So instead, we're going to create a confidence interval to which we can be some percent confident that the true proportion falls between. So to find the confidence interval for the population proportion, which we represent by p, we will use this formula. We will take the sample proportion p hat, add and subtract a z-score multiplied by the square root of p hat times q hat divided by n. P hat is the sample proportion, which can be found by taking the number of successes x and dividing by the sample size. The number of successes in our example will be the number of individuals who could locate Ukraine on a map. Z is the z-score, which we will find using inverse norm. We'll have examples of this later. Q hat is the probability of failure, which is the complement of p hat, which can be found by taking 1 and subtracting p hat. This is the proportion of individuals who could not locate Ukraine on a map in our example. We call the sample proportion p hat the point estimate for the population proportion p. P hat is our best estimate for the value of the population proportion. Z times the square root of p hat times q hat divided by n is what we call the margin of error, sometimes just called the error. The best way to visualize the confidence interval is to write out the number line. We will always have the point estimate in the middle, which in this case is p hat. Then we will add and subtract some margin of error, which is the z-score multiplied by the square root of p hat q hat over n, to get to the lower bound and the upper bound. We would say that we are some percent confident, such as 95% confident, that the true population proportion falls between our upper and lower bounds. Let's take a step back and make sure we understand the purpose of creating this confidence interval. The idea is we would have to have a census of every single individual in the population to calculate the population proportion. This would be like knowing the proportion of all registered voters who can locate Ukraine on a map. We might want to know that value, but it's unrealistic to think that we can calculate that value exactly. Instead, we're going to be calculating a sample proportion p hat, but since it's only based on a sample, we know it's not going to be perfectly accurate. That's why we add and subtract some margin of error to get the lower and upper bounds of our confidence interval. We will be some percent confident that the true population proportion falls between our lower and upper boundaries. Now, in order to construct a one-sample proportion confidence interval, a number of assumptions must be met. First of all, as is the case for all confidence intervals, you must take a random sample. So that means every individual in your population should have an equal chance to be chosen. Secondly, there is sort of a central limit theorem type requirement, which says that the quantities n times p hat and n times q hat should both be at least 5, or some textbooks say they should be at least 10 or maybe 15. This will ensure that the distribution of your sample proportion will be approximately normal by the central limit theorem. Let's take a look at a full example. A February 7th, 2022 poll found that 685 out of 2005 registered voters could locate Ukraine on a map. We are asked to find a 95% confidence interval for the proportion of registered voters who can locate Ukraine on a map. The first thing you should do is write down all the given information and the symbols that go along with them. The value for 685 is X. This is the number of successes, or number of individuals who could find Ukraine on a map. This was taken out of a sample size of n equals 2005. The confidence level is 95%. From x and n, we can calculate the sample proportion, which is 685 divided by 2005, or 0.3416. We'll also need q hat, which is the complement of p hat, or 1 minus p hat, which gives us 0.6584. This is the proportion of individuals who could not locate Ukraine on a map from our sample. Next, we can start to look at our formula, and we'll notice that the only thing that we are missing is the z-score. We can find the z-score in a very similar way that we found the t-score in the one sample mean confidence interval. Instead of using inverse t, we will use a function called inverse norm. And to do this, we're going to want to draw the distribution. Your confidence level should go in the middle, which in this case is 0.95. Then you can fill in the tails with the numbers that make the entire distribution add up to 1. 95 plus 2.5 plus 2.5 does equal 100%. If you're having trouble finding the tail probability, take 100 and subtract the middle probability, so 100% minus 95% would give you 5%, and then divide 5% by 2, which would give you 2.5%, or 0.025 in decimal form. Next, we can go ahead and calculate the z-score. The z-score will be the z-score on the upper bound of our distribution. To get the z-score, we can go to second, distribution, or the vars key, and then scroll down to inverse norm. For the area, we will put the area to the left of the z-score, which is 95 plus 0.025, or 0.975. Always leave mu and sigma at 0 and 1 for the standard normal z distribution, and then go down to paste. Press enter, and you will get the answer, which is 1.96. The z-score that we should use in this formula is 1.96. Next, we can go ahead and plug all the numbers into the formula. We have p hat, which is 0.3416, plus or minus the z-score of 1.96, multiplied by the square root of p hat of 0.3416 times q hat of 0.6584, divided by the sample size of 2005. Let me show you how I would plug this into my calculator. We have 0.3416 plus 1.96 multiplied by the square root of 0.3416 times 0.6584 divided by 2005. Press enter and we will get the upper bound of 0.3624. Next, we can press second and then enter, and then scroll back to the beginning of the calculation and change the plus sign to a minus sign so that we get the minus part of the plus or minus. We will get 0.3208, and those two answers are shown right here. Finally, we can go ahead and write out our interpretation for the confidence interval. The general form of the interpretation that I've used in other videos is that we are C% confident that the interval between the lower bound and the upper bound contains either the population mean or population proportion. So applied to this example, we would say that we are 95% confident that the interval between our lower bound, which was 0.3208 or 32.08% in percent form, and the upper bound of 36.24% contains the, and then in this case we're using the population proportion. So I state the population proportion of registered voters who can locate Ukraine on a map. Make sure to modify your population mean or population proportion so that it applies to your specific example. Alright, we are finished with the problem, so let's recap. The purpose of this problem was to estimate the population proportion of registered voters who could locate Ukraine on a map. But of course, there are millions of registered voters, and it would take a census to calculate that population proportion exactly. So instead of calculating that value exactly, we estimated that value with a sample and calculated a p hat, which ended up being 34.16%. Most likely, our p hat, which we would call our point estimate for the population proportion, is off by a little bit. This is probably not the true population proportion. So instead of just relying on this number, we added and subtracted some margin of error to find an interval to which we can be 95% sure that the true proportion falls between. Alright, here's a problem for you to try. Voter turnout describes the proportion of eligible voters who actually turned out to vote. Suppose you sample 200 eligible voters and found that only 138 of them turned out to vote. Find an interval we can be 99% confident the true voter turnout proportion falls between. So go ahead and pause the video and give this a shot, and I'll be back in just a minute to guide you through a few of the parts to this problem. All right, hopefully you've given it a shot. The first thing that you should have done is written out some of the given information and the symbols that went along with those numbers. So we have a sample size of 200, so that would be our value for n. And from that sample size, we had 138 successes, or 138 individuals who did turn out to vote. So that's going to be our value for x. From those two numbers, we can calculate the sample proportion, 138 divided by 200, which is equal to 0.69. That means that 69% of the individuals from our sample actually turned out to vote. Next, we need to find that z-score. And to find the z-score, you may want to draw the distribution. So I'm going to quickly draw a z distribution here. Something like this. And I'm going to put my confidence level in the middle, which in this case is 99%. So I'm going to put that as 0.99. And if we got 99% in the middle, that leaves us with 1% to split between the two tails. Half of 1% is half a percent, which in decimal form is 0.005, right? 0.01 would be 1%, so 0.005 would have to be half a percent. And then from there, we can find the z-score, which is the z-score on the upper cutoff. And to find that, we can use our calculator. We can go to second distribution and inverse norm. And then we can put in the area to the left of the z-score, which is the 99.5%, or 99.5%, in decimal form 0.995. Leave these two at 0 and 1. Go ahead and paste, and you will get the z-score, which is 2.58. So you should be using a z-score of about either 2.576 or so, or to 2 decimals, 2.58. Usually this is rounded to 2 decimal places, but you can go more if you wanted to. All right, the only other thing we don't have from the formula is q hat, but q hat is of course just 1 minus p hat, so we'll let you go ahead and calculate that. So really all you have to do from this point on is to calculate this value based on all of these numbers, or the upper and the lower bounds from the confidence interval, and then also write a conclusion. So I'll let you go ahead and give that a shot. All right, that's all I had to talk about in this video. Hopefully you found it useful, and I will see you again in the next video.